Welcome back to differential equations. In this lecture, we're going to introduce a technique to solve a type of differential equation called a homogeneous equation. All right, so in our previous lecture, we introduced and solved separable equations. This topic with homogeneous equations, they are not separable, but we'll develop a technique to solve them. So let's start with an example, and eventually we'll come back to solving this, but this will guide us through our intro here. And let's suppose we were to try to solve this by separating. Now we can cross multiply your dx over, multiply your x squared over to the other side, and we get to here, but unfortunately, this is not separated correctly. Recall what we want for a ODE to be separable. It's expressed in this form: a function of y times dy equals a function of x times dx. And in what we have written above, we have variables that are mixed: x squared times dy, and then in the parentheses, we have terms involving y multiplying the dx differential. So the equation above, it's not separated correctly for what we want. All right, now before we move forward, just so we can have some basic and intuitive ideas of what we might want to recognize, notice in that rewritten version, every term seems to be of degree 2. And that's going to play a role in some definitions we give a little bit later. On the left side, we have x squared multiplying dy. X squared is degree 2. And on the right side, in parentheses, we have x squared, degree 2, plus xy. We're going to be a little bit informal and look at that as having a degree 2 term, x to the 1 times y to the 1. Add the exponents, 1 and 1, that seems to be 2. So xy, we'll consider that also a degree 2 term. And then y squared is also degree 2. All right, so that's going to be part of how we recognize if an equation is homogeneous, but let's get back to how we're going to solve this. All right, now let's go back to the original version where we're not going to try separating it. And let's look at the right-hand side and notice that I can divide x squared into each of the 3 terms in the numerator. So we're going to rewrite the right-hand side, divide x squared into each term in the numerator, and we can simplify from there. By rewriting it, we're going to basically see where this technique comes from. All right, if you were to simplify those terms, x squared divided by x squared cancels to 1. The middle term, xy divided by x squared, you can cancel a single factor of x out. And while there are no terms that cancel in the third and last term, we can rewrite that as the quantity y over x squared using exponent rules. All right, so what does this gain us? What can we determine from this? Well, notice on that right-hand side, there's a special combination of how y and x occur. The right-hand side only depends on the ratio y over x. Now, why are we mentioning that? Well, we're going to use that to basically propose what this technique is. Now, the idea is we're going to take an equation that is not separable and try to convert it to one that maybe is separable. How we do that conversion is going to require some sort of mathematical trick. Usually, this trick for converting is some form of substitution. Now, I'm going to keep all this information on the screen for you, and I'd like you to pause and see if you can use this kind of example so far to maybe guide you through what that substitution might be. We're going to use the variable u, like you might have recalled in your Calc 2 course with u substitution, but we're going to use it a little bit differently. So pause and see if you can determine what this substitution might be. What should u equal? We'll check in a few seconds. All right, welcome back. Now, if you notice above, that right-hand side only depends on the ratio of y over x. That might be a good guess for our substitution. So if you guessed, let's try u as y over x. That is exactly right. That substitution is going to lead us to converting a non-separable equation into one that is separable. Now, think back to your Calc 2 course. Anytime you did a u substitution, you calculated the differential du. Differentials and derivatives are very similar. All right, now, while this substitution by itself is going to be used for the conversion, it's not the only thing that we're going to need. All right, now with that, u as y over x, that's part of converting the differential equation to one that's separable. Putting that in above, notice the right-hand side becomes 1 plus u, that's y over x, we're replacing that with u, and then y over x, that quantity squared, becomes u squared. What we have to address is how do we convert the derivative on the left side, dy over dx, how do we convert that properly like we would have done with calculating the differential du in u substitution? So let's address that kind of in a few seconds, but this intro, that basically just leads us to what the substitution is. We'll go through with the details right after this. All right, when you're ready, let's move on. So previously, we just saw where this substitution comes from with that motivating first example. What we need to address is how do we convert the derivative dy over dx, how do we convert that to u? Again, this shouldn't be surprising. Think back to your Calc 2 course. If we were to do a regular basic u substitution, maybe we chose u equals x squared, the differential du would be 2x dx. So differentials, converting that part, plays a role previously. We're going to now try to convert our derivative dy over dx in a similar fashion. All right, now we could use the basic original version that we came up with, u equals y over x, but if you recall that y is itself a function, remember we're always assuming y is a function of x, here we have a function divided by a function. And that would require the quotient rule to differentiate it. Now, there's nothing wrong with using the quotient rule, but it can get a little bit messy. So let's avoid that by rewriting the substitution. Basically multiply x to the other side, and we get this alternate but equivalent version, y equals u times x. Now keep in mind, y itself is a function of x. That means u is also a function of x. But what we have now is a function times a function, and that we can use the product rule to differentiate, which would be a little easier over the quotient rule. All right. Now, I'd like you to make an attempt at that. Keep in mind here that u is a function of x. Pause the video and see if you can implement the product rule here to complete basically what dy over dx should convert to in terms of u. We'll check in about a minute. Welcome back. We're going to apply the product rule. And I'm going to write it all out in detail here. So we're looking at this as u, which is a function, times x. So the product rule would say we differentiate the first function. We don't know what u is, but we'll just write its derivative as du over dx. So differentiate the first function, multiply by the second, which is x. And then we add to that the first function, which is u, but times now the derivative of the second. The derivative of x with respect to x would be 1. So hopefully this is a straightforward application of the product rule. And we can rewrite this. We don't need the times 1 part. And I'm just going to switch the order of x and the derivative du over dx. So what we have here is our conversion for the derivative of y with respect to x. That's now equal to x times the derivative of u with respect to x plus u. Let's summarize this below before we move on to our first example. All right, so we have 2 components, 2 parts to do this conversion from a non-separable equation to one that is separable. Our initial substitution is u equals y over x, or equivalently, y equals u times x. With that, we need to also convert the derivative of y, which is what we just worked out right above using the product rule. And that is something that's often overlooked, and students might forget it, to convert dy over dx to this as well in terms of u. So just keep that in mind. We have to use both of these substitutions. The derivative one, that's just a consequence of y equals u times x. Both of those are required for converting from a non-separable equation into one that is separable. This is our technique for solving what we're going to call and define as homogeneous equations. We're going to save the precise definitions for later, but with these tools, let's get to a first example so we can see how all this works, how this substitution and its derivative combine to eventually lead us to an equation that is separable. When you're ready, let's go to our first example. All right, so this is our intro example. We'll go through this one together. The second part of this lecture will give you some more complicated ones to work on. All right, so we have 2 substitutions, one for the function and another one for its derivative. So let's just use the alternate version, y equals u times x. That's a little bit easier than trying to rewrite in terms of a ratio, y over x. So let's just replace all y's with u times x, and we'll replace the derivative with x times du over dx plus u. All right, we're going to plug these in on the left and right sides. And just be careful with some of your basic algebra here in simplifying the right-hand side. All right, if we were to simplify that right-hand side, that fraction, notice all terms in the numerator contain x squared. Remember from the intro, we said all terms seem to be of degree 2. We're going to save that for the definitions in part 2, but there's some cancellation that occurs here. You can divide x squared into each term in the numerator, and the x squareds would all cancel out. All right, now this still doesn't look like it's separable, but let's clean it up and simplify it a little bit. Notice that the u terms on the left and right-hand side, they subtract out. And it should easily separate from here. So if needed, pause, give yourself a few seconds, see if you can separate this, and we'll check in a few seconds. All right, welcome back. Now, just to be clear, previously we were separating dy over dx. So we would separate that into individual differentials, dy and dx. Here, we're separating it, but with u instead of y. Works just the same. we can multiply dx to the other side and then kind of cross divide to get the appropriate variables of u or x multiplying their appropriate differentials. Okay, so that should easily separate. At this point, that equation has been separated, and now we can integrate both sides. The left side, we're going to integrate with respect to u. The right side, we're going to integrate with respect to x. Now, the integrations maybe will be where you spend most of your time, but here they should be pretty straightforward, as long as you recall some of your basic antiderivatives. The left side, that's going to integrate to inverse tangent of u, and the right-hand side, that will integrate to natural log of x plus c. Remember, we're always going to include the integration constant just on one side. We only need one constant. We don't need plus c and plus d on the other side. All right, so for the most part, this one has been solved, but we are always looking for a solution to a differential equation where we get y as a function of x. Here we have no y's, but they're buried inside of u. So like substitution back in Calc 2, we're going to back substitute u to get it now in terms of what we want. Here, now it's in terms of y and x. So if you plug in u as y over x, we basically complete the problem and we get an implicit solution for the differential equation. Now this one's actually pretty simple to get an explicit solution, solving for y. So just think, how would you undo an inverse trig function? Well, use the regular trig function, take tangent of both sides, and then you can undo the division by x by multiplying by x. All right, that basically brings us through everything for part one. There was basically the intro part to see where the substitution comes from. We then addressed with that substitution how we convert the derivative. And we went through our intro example here, example one. Now this is a nice simple example, not too much algebra, the integrations aren't too difficult, but it does show you all the details involved, how we implement the substitution and how we convert the derivative. Make sure you understand this example before moving on to part two.